let's look at an interaction between two objects that maybe come together and bounce off each other, but let's look at what happens to one of them. As it strikes the first mass, this momentum changes quite a bit from perhaps going this way to maybe going that way or something like that. But the actual interaction is a very, very short thing. The actual amount of time when one object is exerting a force on the other object, in this particular case, is very, very short. But if we're going to end up with a large change in the momentum, we must have a very large force. If it acts for a very short time, we must have a large force to give rise to that change in momentum. Now let's remember, when we were looking at and defining the momentum, what we found was that the force acting on an object was the derivative of the momentum with respect to time, dp dt. And remember, this basically came from taking ma, and a was equal to dv dt, and pulling the m inside and writing the mv as the momentum. So the force is equal to dp dt, and that's kind of another formation of Newton's second law. To do this, to develop this, we actually had to assume that the mass was constant to pull inside here. But the fact of the matter is that when the mass is not constant, this is the form that is accurate as opposed to this one. So we're going to stick with this for now, F equals dp dt. And let's think about how we can apply this to the situation of a rocket. Well, if we have some change in the momentum, let's multiply by dt, and so we have dp equals F times dt. If we want to figure out a large change in the momentum, or the total change in the momentum, we would integrate both of these, and this is going to give us the total change in the momentum is then the integral of F dt. Let's think about what this force looks like. When we have some kind of interaction, typically we'll have a time when there is no force, and then force, there is a force, but then no force, no force, no force. So the force as a function of time, in general, will look something like this. If we graph the force as a function of time, there is going to be some limits that before some initial time, we'll call this t1, we have zero force. And after some final time, call it t2, we have zero force. But then in between, the force gets large and then decreases and is zero. So it's during this time from t1 to t2 that we actually have the force of interaction taking place. So this integral of f dt is going to give us what? It's going to give us this area, the area under that force curve. That is called the impulse. Whoops, sorry. And we write that as the vector I for impulse. The integral of f dt from some limits that will cover all the time when the force is actually non-zero. So the change in the momentum is equal to this impulse. The impulse that we calculate by integrating the force dt, that gives us the change in the momentum. Now, let's take a look at how this works with, as I said before, a rocket. How does a rocket actually work? It works because of the conservation of momentum, and we'll see how. Here is the basic situation that we have for a rocket. Let's imagine we've got a rocket here with a mass m that at some time t is moving at some velocity v. The rocket is burning up fuel inside and shooting the exhaust out the back. So the rocket is losing mass. The mass of the rocket is decreasing as it sends out more burned up fuel exhaust out the back. So sometime later, at t plus delta t, the mass of the rocket will have changed. It's going to be a new mass m plus delta m. But let's keep in mind, delta m is negative because the change in the rocket mass is negative. It's decreasing its mass. So delta m is negative. That decrease in mass is the exhaust that's being sent out the back. So let's assume that the mass of the exhaust is minus m, whatever that change is, the negative of that, so that the mass of the exhaust is actually a positive quantity. The rocket, because it's a kind of a uniform burning, the mass that's being ejected is ejected from the rocket at a relatively uniform velocity relative to the rocket. So let's imagine that it is being ejected at a velocity u exhaust, but let's keep in mind that is relatively constant, but it is relative to the rocket. It is not relative to, say, the atmosphere or the Earth or something like that. And let's keep in mind that u exhaust is going to be negative. So the direction of this is actually backwards, in the opposite direction to the motion of the rocket. So if that is the relative velocity, remember, how did we find relative velocities? For example, when we were looking at the motion in the center of mass, we subtracted off the velocity of the center of mass. So this relative motion must be the absolute velocity minus the velocity of the rocket. So to get the velocity relative to the Earth or the atmosphere back again, we have to add back in the velocity of the rocket. So the velocity, of the exhaust relative to the Earth atmosphere will be ux v plus delta v. Okay, so we have to add in that v plus delta v to get the absolute velocity as measured by the atmosphere or the Earth, something like that. Okay, there we go. Now, let's figure out what are our momenta. What's our initial momentum? What's our final momentum? And then whatever difference those have must be due to the external forces. So what do we have? We've got P initial will be mv. Okay, and P final will be, well, we've got two things here, the rocket and the exhaust. What is the final momentum of the rocket? Well, it's going to be its mass, m plus delta m, times its velocity, which is v plus delta v, and then plus the momentum of the exhaust. So plus the mass of the exhaust, which is minus delta m, times the velocity of the exhaust, which is v plus delta v plus u exhaust. So v plus delta v plus u exhaust. Okay, there we go. Let's multiply this out, and we get mv plus m delta v plus delta m v plus delta m delta v. Okay, that's the product of these. Now let's multiply these here, and what do we get? We get minus delta m v minus delta m delta v minus delta m u exhaust. Okay, there we go. Now let's notice some things will cancel out here. We've got a delta mv minus delta mv, so these cancel. We have a delta m delta v minus delta m delta v, those cancel. Okay? Now, let's look at the change in the momentum, delta p. Remember, delta p is equal to the impulse, which depends on the external forces. So, delta p, which is p final, minus p initial, will be equal to, we're going to take this result and subtract p initial, but p initial is mv, and that's going to cancel the mv here. So that's going to cancel those there. And what do we get? We are left with m delta v, and then minus delta m u exhaust. There we go. What does this equal? The change in the momentum equals the impulse. And remember, the impulse is then the integral of f dt, or we'll just say, because we're talking about macroscopic changes here, F delta t. Now let's divide by delta t, and what do we get? We get F delta t. Oops, sorry, I mean, we're dividing by the delta t, so we get F equals m delta v over delta t minus delta m over delta t times u exhaust. Great. Remember, what force was this? This was the external forces. So let me just emphasize that's the external forces. Okay, great. Let's bring this term over here, and let's take the limit that delta t goes to 0. As delta t goes to 0, this is going to turn into dv dt, and this is going to turn into dm dt. And what do we have? We have that m dv dt is equal to F external plus dm dt times u exhaust. There we go. Now, let's just notice we've got a little change here. It's kind of an important change from Newton's second law. We might have thought that the F external was equal to m dv dt all by itself. dv dt is a, right? So ma, F equals ma. But because of this changing mass, we have this other term, dm dt times the exhaust velocity, the velocity that the mass is ejected relative to the rocket. Let's take a look. What's the solution of this? Can we solve this and kind of figure out what's the velocity of the rocket going to look like? So let's remember what we have. We've got the rocket with a changing mass, m plus dm, infinitesimally. The velocity is changing, v plus dv. We've got the exhaust mass being ejected out the back at some relative velocity relative to the rocket of u exhaust. And what we found was that m dv dt was equal to F external plus u exhaust dm dt. This is called the rocket equation. Now, we would think F equals ma, right? What is this term? Where is this coming from? That is actually an additional force acting on the rocket due to the exhaust being thrown out the back. This is called the thrust force. This is acting just like a force on the rocket. It is what is pushing the rocket forward. Let's see if we can solve this under some simple situations. Let's imagine that basically this is the y direction. So we've got the Earth. Maybe the Earth is back. Oh, if you can see the Earth, I don't know if I'm off screen. So here's the Earth back here. So this is the upward direction away from the Earth. So the velocity is in the y direction. The external force, what's that? That's the gravitational attraction from the Earth. What's the gravitational attraction acting on the rocket? It's going to be its weight. So the force is going to be minus mg, acting backwards. And then the exhaust velocity, that we know is in the negative direction. And so we will take that as negative u y hat. So we're going to write this as a scalar equation, removing the vector signs and putting in the signs, removing the vector signs and putting in pluses and minuses to indicate the direction. So let's do that. So we have m dv dt equals gravity in the negative direction, minus mg, and then exhaust velocity is in the negative direction relative to the rocket, so we'll write this as negative u exhaust dm dt. Let's multiply by dt and divide by m. So what do we have? We end up with dv, divide by m, multiplied by dt, equals, divide by m, multiplied by dt is minus g dt, and then multiply by dt, divide by m, and we have minus u x dm over m. And now we're going to integrate. We're going to integrate from some initial position to a final position. So we'll integrate from v initial to v final. from some time, T initial to T final, and then some mass, M initial to M final. Okay, there we go. What's the integral of dV? That is just V, evaluated from V initial to V final. Equals minus G, what's the integral of dt? That's just T, evaluated from T initial to T final. Minus U, exhaust. What's the integral of dm over m? That's the logarithm of m, the natural log of m. So that is natural log of m evaluated from m initial to m final. Okay, there we go. Let's stick in these values. What do we have? We have v final minus v initial. That is going to be delta v. Or we'll write it as v final. We'll just write it as v final minus v initial. Equals minus g times t final minus t initial. That we'll write as delta t. Okay? And then minus u exhaust of log m final minus log m initial. The difference of logs is the log of the ratio, so we'll just write this as m final over m initial. So we've got a negative sign. We'll pull that into the log and flip the masses around. So we'll make this plus and make this initial over final. Okay, there we go. And there is our final result. Let's rewrite. Let's get rid of this and rewrite that. Okay, let's take a look at this final result. Vf minus Vi. What is that telling us? It's telling us the change in the velocity of the rocket. How does the final velocity of the rocket compare to the initial velocity of the rocket, say, after it's burned all its fuel up? It's going to be equal to the exhaust velocity times the log of whatever the initial mass is divided by the final mass, and then minus g delta t. So this term g delta t, that is taking away from our increase in velocity, because the longer the rocket is near the Earth, the more the Earth is the more time the Earth has to decelerate it, so to speak. So the more it's going to decrease the velocity. Yeah, okay, that makes sense. Let's look at this part here. This leads us to a very interesting problem regarding rockets. Let's imagine that we have a rocket, a very large rocket, that is, let's say, 90% of the rocket is fuel. So we arrange our rocket to have a small amount of space for the astronauts and things like that, what is called the payload. The payload of the rocket, while the rest of it is fuel. And let's imagine that the part of the rocket, after all the fuel is burned up, is maybe 1/10 of the full fuel, the rocket full of fuel. So let's imagine that the initial mass is, let's say, 10 times the final mass. So 90% of the mass is fuel that gets burned up. So what do we get? Well, this term here, ux, log of mass initial over mass final, will be ux log of 10 mass final over mass final, which is log of 10, which gives us 2.3 times the exhaust velocity. Okay, so if we use up 90% of the rocket as fuel, we will end up with a final speed of 2.3 times the exhaust velocity, minus the g times delta t. Well, what if that's not good enough? What if we want it to go faster? Well, let's imagine that we make a rocket that is 99% fuel. So in that case, mi is 100 times the final payload mass. So the rest of it is all fuel. 99% of the initial mass is fuel. So what do we get in that case? We end up with ux equals log of 100 times the final mass over the final mass, which is, times UEX times log of 100, which is 4.6 UX. We're only going twice as fast. We've gone from a rocket with 90% fuel to 99% fuel, and we've still only got up by a factor of 2 times the mass, 2 times the speed of the exhaust velocity. Well, that's a big problem. So how do you get rockets to go fast? Well, one of the things that you can do is you build them in stages. So after the fuel has burned up to some extent, part of the payload of the original rocket would drop off, or so it's not payload anymore. So part of the rocket actually drops off, and then during the next stage, you're not accelerating that wasted mass. See, when you've got a lot of rocket fuel, you've got a lot of rocket fuel that you need to accelerate. So you've got to get rid of some of that mass, and what you can do is you can get rid of the part of the mass that's actually storing the fuel, and then it goes some more, and then you can drop off another part of the fuel and let that go, and then you don't have to accelerate that anymore. So that's one way of increasing the velocities. All right, very, very good. Wow, that was a lot for this lecture. What we're going to do next time is start looking at another type of two-dimensional motion, but motion when something is going around in a circle, rotational motion. And we're going to look at rotational motion in some detail, in all sorts of very, very interesting situations. All right, see you next time.